Welcome back, coders. I'm going to be re-uploading the code for the last video. So if you want to read that explanation with the code samples and so on, this is the video for you. All right, let's get started. Okay, so in the last video, I didn't take into account that YouTube wants to upsell their enhanced 1080p bitrate and they downscale your video on purpose. So what I'm going to do in this video is I'm going to be screen capping the code with a much higher resolution so that when you upload it, even if they downscale it, it looks okay. Alright, so I'm going to leave the same thing as the previous video. I'm going to leave the premise here, and you can read it if you pause the video. And then you get the example constraints and considerations, and then the evaluation criteria at the end. So let's look at the code now. Alright, so let me run this code like this, I guess, just to see if this is working. Yeah, it's kind of working. Do it again, just to check that it does. Yeah, all right. All right, let me explain the code for the naive novice. I guess this is what you couldn't see in the last video. So I'm taking the input, I'm making a defensive copy of this, because if I work on these elements, I'm going to be messing with the original array. So if you send that to the next solution and the next solution, you're going to have different elements. So I make a copy just for myself. I'm going to try to make this from the point of view of an interviewer, so that you can know how the interviewer is thinking and what they're evaluating for. First thing, they want to know if you sanitize your input, if you check it, if you are expecting or if you're going expecting the wrong input and trying to do the right thing with it, because that also speaks about maintainability and testability. You're taking into account those corner cases, and you're trying to make it fail safe. So we are checking that the input is not already in its minimum form, which is all the elements are 1. Then we're going to start going as we had in our plan of attack. For each day, find the maximum, make a decay, so halve it. And the second criteria for evaluation is to return the sum of the inventory. So we sum the result of all the elements. And then we keep going until all elements are 1, and then we're just going to be counting the days to cover number 3, like so. All right, so we sanitize our input, we go again for each day, go through all elements, trying to find the maximum and recording not only the maximum but also the position in the array. We check if that maximum is 1. If it is 1, that means we reached the minimum state of all the elements, and that's why we're counting the real days, because we might take fewer days than originally requested, right? So if these days are too big and we don't need as many days, you want to be counting how many real days you took. Don't always assume that you're going to be able to perform the action you want with the input parameters you get, right? If the maximum is not 1, then you have 1 more day to make the elements decay, and you take the place where the maximum was and you're going to take it out, remove utmost half, and then put it back in, basically. So that's why you're taking it out, removing half, and putting it back in. You report which day you're on, which element you selected for decay, and what's the status of all the elements after it decays. For the second part, we get we concatenate all the numbers with a plus in between, and we also add them so that you can get a nice formatting of after the real days you took. The sum string only has all the elements that you have in the array after the real days, concatenated with a plus in between them, and then the final sum. That covers number 2. For number 3, now what we have is we're going to be counting the days until we get to that minimum state of all the elements being 1. We assume there's no, so we take the minimum always, and then we're going to be replacing it with the maximum, just like we did in the first part. For all the elements, we find the maximum. If that maximum is 1, then we have reached a state of where we have reached the minimum state where all the elements are 1. And if we haven't, then we count one more day of decay, do the same thing as we did in the first part. We make the element decay, and you might or might not report which element was made to decay on what day and what's the state afterwards. Right? After that, you report how many days you took, which is the real days and the rest of the day. This is a perfectly good solution. So if you show this to a recruiter, I mean, you can always improve on it afterwards, and they probably want to see you after you finish it, after you did it correctly. They want to see you improve on it, right? And that's sometimes where people get confused. Like, yeah, you might see this code and say, but that's too naive, and it doesn't matter. It does the job. It's understandable. It does the job, and you can rest assured that someone comes and reads the code and they're gonna understand what's going on. They're not gonna pay you to be clever. They're gonna pay you to solve problems. They don't care how clever you are solving something, unless it's too tricky that you cannot solve it in a naive way. Solving it this way is perfectly fine. All right. Now we have the naive intermediate. As you saw, we're iterating over all the elements to find the maximum. In this case, we chose to stop iterating over all the elements, and instead of doing that, we're going to use a data structure that it's called a max heap. It keeps elements sorted, and you can in this case, we're sorting it in reverse order so that we get the biggest at the beginning, and then it's going down until you get to the smallest. You get all the elements and you put them inside that priority queue. We peek at the first element without removing it. We ask if it's 1. So as you can see, now we're not going over all the elements to find the maximum and then finding if that maximum is 1. Give me the first one, which is the maximum. And if it's 1, we're already at a minimum state. So doing exactly the same thing as the previous solution. Same thing here. We have replaced the looping through all the elements to find the maximum for just queue pull. And this data structure is going to be responsible for maintaining that order. This is exactly the same. The way you make the element decay is a little bit different. That's just, we take that maximum, remove utmost half, and then just add it because we removed it here. So it's 1-to-1, exactly the same thing as in the previous solution. But if you look down here, you can see the difference just using a more elegant data structure or a more appropriate data structure makes when it's the same input for both. But since this is maintaining that order, we don't have to loop through all the elements. Now that we have a data structure, we could still do it by iterating, but if we want to get the nice adding of the of all the elements, like, well, not exactly like this, but if you want to know the elements you're adding, just gotta stream the elements, convert them to string, collect them by joining them with a plus in between, and that's it. And you can do this in a different if you want it, so it opens up your option a lot more. You can even make it parallel if you want. I don't know in this case if it's gonna help or not. You're gonna have to try. Sometimes you might try it and it's gonna be worse, so I usually try to keep it simple. And the same thing for adding the numbers. So this is just to generate the string, and this is to add the numbers proper. So I'm converting it to an int string and then doing sum, and that's it. For the third part, in the naive intermediate, same thing. Remove the first element, check if we're at a minimum. If we're not, there's one more day of decay. We make the element decay and then report. Finally, you tell the caller how many days you took to get all the elements down to 1, which is the real date, the first evaluation criteria, and this third one. The naive advanced, this is almost the same, except that you're checking for input. Now, instead of doing it one by one with the looping, I'm gonna create a record with the day we're on and the maximum for that day. I'm gonna try to create a range from 0 to days minus 1, which is exactly the same as using the for loop. I'm gonna map it to that record I created here. That record has the peak of the biggest element. I'm gonna say, okay, the minimum is gonna be if that first weight is 1. And why is this an array and what's going on here? In order to access something from the outside here inside, this has to be final or effectively final. And the little hack I got is just to make it a final array, and it has a single element. It's just like the boolean. And this is why doing the clever things sometimes it's a bit hacky, and I don't like how this looks. Like, why are you using an array? It makes me have to think about what I'm not what I'm solving, but how I'm solving it. And in the future, whoever reads this wants to modify it or add or remove functionality, they're not only going to be solving the original problem, they're also battling the solution itself. So you first battled with the problem, you got to the solution, and now you got to battle with the solution now to just improve on it. This doesn't open many avenues of improvement. All right, so you check that you're not at a minimum. You ask if the element can be made to decay. If it can, then what you do is you make it decay just like we did in other previous 2 solutions. And if you haven't reached the end, well, and you count, right? So you have 1 more. Go back next day, do the same thing. If you get to a place where you cannot make the element decay, this doesn't get to the end, so it doesn't get counted. You can still keep going, but it doesn't keep counting the other days where you cannot make the elements decay, right? So you count them, you get the real days, you make a final check to see if you got to a state where you're at a minimum. You get the sum of your inventory for the evaluation criteria number 2. And for number 3, you start where you left off. This is the starting position, so real days. You're gonna keep doing this, iterating, until you reach a minimum. So while you're not at a minimum, you keep generating numbers. And how you generate the numbers is you take the previous ones you generated and add 1. That's it. So you can be doing real days plus 1, plus 2, plus 3, plus 4, so on. How does it know it got to the end? Because you got to the minimum. So this is doing almost exactly the same thing as the while loop we had in the previous solution. Same thing, map it to a new day without removing the maximum. Check if you're at a minimum with our hacky one element boolean, ask if you can make the element decay. If you can, you make it decay and you count. Same thing. Then you report. Why is this hacky? And I said it in the previous one. Well, why is this a boolean array? Why am I using this way of counting things and peeking and filtering, and what does this give me? I cannot do this in parallel anyway. What do I gain by using a stream that I cannot have by using a normal for loop? So it's something to think about. I mean, yeah, if you look at the performance, yeah, it's a bit better. I mean, you could say that it could become a lot better because the compiler can make clever decisions and not execute parts of the code or whatever. But if you show that to the interviewer is going to be, if they don't understand it, I mean, it's going to be hard to convince them that it's maintainable code, right? Now that we did this, we're going to step back and we're going to see, okay, we have been dealing with single elements along the way, and this is supposed to be the inventory, right? And when you think about an inventory, you think about how many items I have for each product, right? So in this case, how many elements I have with the same weight. And if you start thinking like that, then what you need is a way to make a histogram of the weights you have and the frequency of those weights. So how many times you have seen one element of weight 20, and how many times you have seen elements of weight 19, maybe 3 times, and elements of weight 18, maybe just 2 times, right? To generate that histogram, I'm going to use a sorted map because I want to have the weights sorted. You could make this histogram without using a sorted map, just a regular map, but your inventory is not, the weights in the inventory are not going to be sorted. So the buckets are going to be sorted. We use the same comparator for the priority queue. We stream all the elements and we convert it into a map where the key is the weight, and then we count how many times we have seen elements with that same weight. And in this case, we're just thinking about, all right, so it's an inventory, and that's how we got to this solution. So if you're in a coding challenge, yeah, take it. First, make your plan of attack like we did at the beginning. Start with a naive solution, but keep it on the back of your head and think about it while you're solving it with the naive solution and say, we should make a real inventory. And that might open up a way for us to do things more efficiently. All right, so we generate the histogram. Still checking for input. You might want to check more or less. I'm just doing a simple dumb check. So this isn't even everything you can check. You can check if the elements that you have here, in this case, they're ints, so they cannot be known. But if they were objects, you would need to check if the array exists, if it's initialized, if all the elements are okay, if they're not null. So there's a lot more that you could be doing, maybe even inside the generate histogram, so that you can move that also out of the way, or having its dedicated check input, validate input, or something along those lines. We go back to our old friend for loop, and we leave behind all the streaming nonsense that we had in the naive advanced solution. So we take the biggest, which is the first key. We calculate what the weight after the decay is going to be. And then we compute new values for the biggest and new values for the weight after the decay. This takes the place of, we're going to be removing one element. So if you had 5 in the frequency, you have seen 5 of a specific weight. Now you're going to have 4. If you had a single one, you're going to remove the bucket altogether. So you don't even want to have 0. And once you make it decay, you're going to have to calculate new values for the weight after decay, because if you make one element decay and the element is 100, you're gonna remove the 100, make it decay, and then put back 50. You might already have a bucket with elements that weigh 50, right? The new values for the elements that weigh 50 is, if it didn't exist, now you have one. If it did exist, it had, let's say, 4, well, now you have 5 because I made an element with 100 decay, right? You count the days you have made elements decay, report it, you ask if you're at a minimum, and I have extracted here the way to display the sum of the elements and the little joining with the plus signs in between the elements. And this, you only get to understand this once you start solving problems in multiple ways, so that you can see and compare the benefits of one solution versus another solution. So what I would recommend is, if you go to LeetCode, HackerRank, or whatever you practice your coding challenges, try to make a solution and then try to keep going. Try to make another solution that is different. Try to see it from a different point of view. Maybe change the paradigm, so instead of having those arrays of elements, you convert it into other data structures. You think about it like we did here. So, oh, we do have an inventory now. This is an inventory. That allows you to have pieces in common that you're always going to use in no matter what solution you have. And then you can make sure that, all right, so I'm going to extract that because that seems like it's not going to change. All right, now, once we have done the first and second parts, we're going to do exactly the same thing we were doing before. In this case, we don't care about the how many days are left, so that's why we don't have a for loop. We only have a while. We're going to be counting the days that we make elements decay until we find the minimum, and that's the whole idea of this while loop. This is exactly the same as the first solution, right? And that's why you see it here. It takes sometimes a little bit less, sometimes a little bit more, but more or less it does the same thing, right? It just does it in a more elegant and readable way. So this solution, performance wise, it's going to be almost the same, maybe a little bit slower than the naive novice, but it's much more readable, and it opens up an avenue of improvement that you didn't have before, right? Which is, now that you have a real inventory, you don't have to deal with the array of elements, having each element individually. So your space is reduced the longer you run this these loops, right? So that's another thing. You're on an interview, you're gonna be working with your big O notation. You're in both the amount of steps, so the performance, but also in space, so the amount of memory you're using. If I have this, and I say I have 98 items with weight 1, this arguably takes less space than having the same, but having the object 1 repeated 98 times, right? Maybe the overhead of the map and that doesn't have a chance of competing with a native array, but the bigger this gets, then maybe you get benefits out of it, especially because this is a sorted map, so you don't have to go over all the elements to keep them sorted, or you don't have to figure out how to get the maximum, right? That's something less that you have to worry about, and something less that your colleagues are going to have to worry about when they see the code. Now, if we go to the advanced, this looks a lot smaller, right? Why does it look smaller? I just extracted things. I took notice that in every solution I had solving the first part, solving the second part, solving the third part. And I said, all right, let me just try to extract the parts. And this looks tidy. Do something the first part, do something the second part, do something the third part. How do we solve the first part? We still process our elements to generate our inventory. Okay. I should have called this convert to inventory. So make sure you name things properly. Don't be afraid to put long names on variables, because that's going to make it a lot more clear for the interviewer that you want them to understand what you're doing. I'm going to make the elements decay at most this number of days. This might be the original number, so let's say 5. I'm going to be still counting the number of days. I'm going to check, okay, I have these days remaining, and while those days are not 0, I'm going to keep going. I take the biggest one. I take a picture of how many days I had before I tried to make them decay. I tried to make them decay, and if the remaining days you have are the same as the days you had before you started making the elements decay, that means you didn't use any day. So you're going to break from this loop, and I'm going to explain what that means. What I'm doing here is I'm checking, this is checking for input, checking for input, checking for input, just validating that my input is correct. And once I validate that my input is correct, I perform my operation. If the frequencies, if the map is null, if I don't have any elements in the map, or if the keys and values for that entry are null, or even, and this is our particular check for this particular problem, if the biggest is not greater than 1, then we don't have anything to do here. We cannot make elements decay, we cannot do anything. So in any of those cases, you gave me a predetermined number of days I could use to make elements decay. I couldn't use any of those days, so I'm going to return the days to you. Like, I didn't use any of these days, so here you go. If the validation is passed, I'm doing exactly the same thing as you saw in the intermediate solution, but I'm going to take advantage of the repetition I have seen in the elements since I now have an inventory. If the biggest element is 98 and you have 3 elements and you still have 5 days to go, the first day you're going to pick 198, and the second day you're going to pick the second 98, and the third day you're going to pick the third 98. So you already know what you're going to do the next 3 days. There's no mystery. What we should do in this case is, instead of going day by day removing and making it decay, all of them are going to decay in exactly the same way. So you could take all 3 of them and calculate their final values after 3 days, and then put them back with their frequencies after 3. So you're moving in time 3 days ahead. You don't have to check each day, right? In this case, it's exactly the same way, but we have to change the way we compute the frequencies in the bucket. Before we had, if the frequency was 1, we would remove it, and if not, the frequency would be lowered, decreased by 1. Now we need to have a limit of the number of days that we can operate. If you have 5 days to go and 3 elements, you can only take those 3. You cannot take 5 elements. And in the opposite case, if you have 5 elements but only 2 days to go, you can only take 2 elements. You're not going to take 5 elements because you can only make 1 element decay per day. So you have 2 days, you're going to take 2 elements. So you take the minimum between the biggest frequency, which is the value of that biggest element, and the number of days you have to go. So the minimum between the two is how many elements you're going to make decay. If the frequency is exactly that number, that means you're going to remove the whole bucket. If not, then you're going to take the frequency you have and lower it by that number of days. So if you had 5 elements and only 2 days to go, you're going to lower that 5 in 2 elements. So you're going to be left with 3. That's how you remove. Now you have to put the decayed elements back. And you're going to do the same thing. You're going to be computing what the frequency would be for the bucket where the weight is, the weight after the decay. If you didn't have a bucket without that frequency, you're going to create one having this value, the day limit. That means you remove n number of elements from one bucket, made them decay, and now you have a new bucket that you didn't have before with the same n number of elements. If you did have a bucket already with that number of elements, what you're going to have is whatever frequency you had before plus the elements that you make today. And you're going to return how many days you used, right? So if I had 5 and I only used 2 days, then you're going to return 3. So those are the days that they can still go. And this is why you're checking in here how many days are remaining. If you send 5 and you get 3 back, you still need to go and try again, right? And you're going to try to keep going until you find a way to get rid of all the days you had to go. You still report which element decayed on which days. In this case, now you're not making it day by day, so you can compact the output even more by saying, okay, I took this element and I did it, I made it decay this many times. And you can see this here, for example. So you had 30 elements of weight 6 as the maximum, and you took that step of going from day 304 to day 334 because you made that element that weighs 6 decay 30 times because you have 30 elements. So you took the first element that weighs 6, made it decay, now you have 3. And that's something that you can see here. You didn't have a 3 here, and now those 36s become 33s. You see? You made them decay from 6 to 3. You take the same approach here. This 5, you make it decay 38 times, and you make this jump. And the 5 is something that you made decay from 5 to 3 again. So as you can see, you had 30, now you have 38 more, you have 68. And this is another advantage of this solution. That means since all of them need to get to a minimum where all the elements are 1, this is where the what I mentioned in the previous video about pigeonholing. When you have buckets for numbers from 1 to 100, you have 100 buckets. If you have 1,000 numbers, that means you have repetition. You have multiple numbers are going to be in the same bucket, right? And that's exactly what we want here, because this is an inventory. If your numbers are capped at some number and you have fewer buckets than elements, you're going to have to make the bucket be shared by multiple elements. And since we're making the elements decay always picking the maximum, that maximum is capped, and it's not only capped, but it's going down. That maximum is going down. So you can see here, the maximum was 33, that's 31, that's 29, 28, 27. This is going down. The elements in that you make decay, with the example of 1 to 100, for example. If you have numbers from 1 to 100, then you know that when you make them decay, they're all going to have to fit between 1 and 50, right? And after you get that where the 50 is the biggest one, you make them all decay, they're going to have to fit in 1 to 25. And you can see they're going to start sharing the same buckets until you get to the very end where they're all in the same bucket, right? And this is why you cannot make this part, the third part, in parallel, because if you make it in parallel, what you will be doing is, I don't know how to say it, but you wouldn't be taking into account the decayed elements, the weight of the decayed elements, and you would get a less efficient less efficient plan to make the elements decay. Because if you had let's say we had this, for example, do you know that if you take this one and you make it decay once, you're gonna get 3. If you're gonna make it decay again, so that's 30, 30. If you make it decay one more time, you go to 2, from 3 to 2, and then from 2 to 1, right? So that's 3, 2, 1, 3 times. This is the same thing. From 5, you go to 3, 2, 1, 3 times again, so that's 6. 28, 2 times only, and 2 times, or actually 1 time. This is 1 time only. So 3, 3, 2, 1. So those are 9, right? If you multiply each number, because you can only make one element decay, So what you're gonna have here is 30 times 3, that's 90. This is 90 plus 24, that's 114. Plus these 90 is 204. And then this is only 2, so that's 56. 260. And this is 262. If you check the number you have here, 304 plus 262, what do you get? You get this. You see?
Are you delusional? Do you suffer from a mental illness?
And I didn't have to iterate over anything. I just said, multiply this by log 2 of this number and do that for all of them. That's it. No looping. Just straight through each element and just calculate how many steps I need to make them decay to the number I want, which is in this case is 1. If you take the log base 2 of this number, that's what you're probably going to get 3, or you can tweak it until you get what you want. And this only happens because we're making it half and half and half. And this leads me to the final advice. Make it clever, but not as clever, because after you finish solving it, the interviewer is probably going to be asking you, oh, what would you do to make it more efficient in, I don't know, in space, or more time efficient, or I don't know, some other metric. So try to make it simple, understandable, and keep your options open. If you keep your options open, then you can start evaluating paths, right? Oh, just like I said now, instead of at the end doing a while loop and trying to keep the buckets in position, forget the buckets, take the whole thing, just get the log base 2 of that and multiply by the frequency, you're done. That's it. No need to do all of this. You could have a single step with the whole thing done. And actually, we might be able to check it here. All right, so this is making the balance decay in the first part, displaying the thing. For the third part, I'm gonna show you this, and then now I'm gonna edit it so that you can see if you use the log base 2. This is the same thing. You count the days, make elements decay, but now you don't care about how many days you have left. You just care about, is this the minimum? No, keep going. Is this the minimum? No, keep going. And once you reach the minimum, this is how you report it back, exactly the same way. So let's try display name, display days on total decay. Let's not do this. Let's take the frequencies and get the entry set and parallel stream it, and then we're going to be mapping it. So you have an entry, and the entry is the bucket, and you're going to be returning the bucket dot get key. We need to get the log base.
A few moments later.
2 of this, which would be math.log. This is a natural log of the bucket get key divided by the math.log of 2, I guess. I would do it. This, I want an integer.
12 seconds later.
Oh, it's supposed to be. Right, we don't really need to do this. We just need to calculate how many steps you need to make all of that decay. All right, and if you like this video, or if you want to if you have your own coding challenges that you want us to review, just send them over. If you have an interview yourself, well, good luck and happy coding.